Hello everyone, welcome back to your favorite place, the Statistics Fun Room. In this video, we're going to take a look at the concept of the Central Limit Theorem. Now, Central Limit Theorem is extremely important, extremely exciting, and it's going to be the basis of everything we do throughout the rest of our videos, throughout the rest of our course of Introduction to Statistics. And just as a quick reminder, the basis of this course is that we don't typically have access to the population data set. So we do sampling. Based on our sampling, we have some statistics that describes that sample, a mean, a standard deviation, a median, things of that nature. We're going to typically focus on mean and standard deviation. Now, once we take a sample of our population, we want to be able to make predictions or draw inferences about our population data set based on the sample. So in the prior couple of videos, we were discussing the normal distribution, the symmetric distribution, the Gaussian distribution, and we were using that distribution to find probabilities within any particular data set. Now, technically in those videos, we were using population data, which really isn't realistic. But the reason we were using population data was to get our hands dirty, right? To get comfortable with how we find probabilities of normally distributed variables. What we're going to start to do today and throughout the rest of the videos is look at the more realistic situation that we are taking a sample of a data set, and based on that sample, we're going to make predictions about the population, which we typically don't have access to. Now, the concept in this video is, again, the Central Limit Theorem. And here's basically what the Central Limit Theorem says. I want to look at this simulation which illustrates the Central Limit Theorem, and then we'll come back to our note page and we'll write some things down specifically. So to illustrate this concept, I'm going to look at this simulation. So in the simulation, we're going to suppose we know the population. Here's my parent population. We're going to suppose we know that it is normal. Now, the idea here, right, the Central Limit Theorem is I'm going to build a sampling distribution. So for example, let's suppose I want to look at the average of every sample. And let's take samples of size 25. So here's my population. I'm going to randomly sample 25 data points from that population. So here come my 25 data points, and then once I sample those 25 data points randomly, I'm going to find the mean and then plot that mean. Now, what does this data set represent? I don't know. Let's make something up. Let's suppose this data set represents the height of human beings. So if I measure the height of human beings, I have just sampled 25 human beings, measured their height, and found the mean of that sample. And the concept of the Central Limit Theorem is I'm going to continue doing that sampling process. So I'm going to animate this one more time. Here's 25 other people that I've randomly selected, measured their heights, and then find the mean of that sample of 25 humans, and there's that mean. Now, ironically, the mean turned out to be exactly the same, but that's not always the case. I'm going to do this one more time, hoping the mean comes out to be different. So this is what we're considering the distribution of sample means. So I'm going to take a bunch of samples. Wow, check that out. The mean is the same. So here's what I'm going to do. I'm going to hit the number 5. And what this is going to do is find 5 samples of size 25. And it's not going to animate. So there's 5 new means that we just plotted. So if I do 5 more samples of size 25, plotting each of the means, what we're building down here is a distribution of all the sample means. So we can see the title here as the distribution of the means of each sample. Now let's suppose I continue doing that. So I'm doing groups of 5 samples each time. And as we continue doing 5 samples, what we're going to notice is our distribution of the sample means is becoming proximately symmetric, proximately normal. And the more and more samples that I take, the more normal the distribution becomes. I'm going to stop right here. I have 558 samples that I have taken. So out of my 558 samples of size 25, the mean of the distribution of sample means is 15.62. And the mean of my normal distribution of my population was 15.75. So we can see that these are pretty close. So the mean of all of the sample means is almost equal to the mean of the population. And that's going to be one of the statements we make in the central limit theorem, that they are equivalent to each other. So in theory, the mean of my distribution of sample means should equal the mean of my population. Now in practice, they'll typically be a little bit different, but in theory, they're the same. Now, what's really unique, so first of all, this shouldn't be very surprising that when my population is normal, my distribution of the means of the samples is also normal. That doesn't seem very surprising. But what's really kind of unique here, let's say I do a skewed right distribution. Notice this is skewed right, and the mean is 8.08. Now, if I continue doing samples of 25, I'm just going to do a whole bunch of samples of size 25. You can already kind of start to notice that the distribution of sample means is approximately normal. I'm just going to do 10,000 samples, and I can see my distribution is very normal. It's very symmetric. Now again, the central limit theorem is going to say the mean of this distribution of means should equal the mean of the population. And we can see that they're really close, not exactly equal, but theoretically they will be equal. So 8.11 and 8.08. So this is pretty cool. When the distribution of the population is not normal, it turns out that our sampling means have a distribution that is normal. So this is really powerful. We can continue using the normal distribution, the standard normal distribution that we used in the prior couple videos, and apply that to my samples. All right, so let's write out a formal statement of our central limit theorem. So just back to our original beginning of our conversation, when my parent population, right, when my population is normal, the distribution of sample means was normal. The mean of my distribution of sample means is pretty equal to the mean of the population. Now, I stole this out of a textbook because I love the visualization. And here's what the first part of the central limit theorem says. It says, if our population is normal, my distribution of sample means will also be normal. And it says that this is true for any size of samples. Now, if I come back to my sampling distribution, we did samples of size 25. The central limit theorem says we could do any value of n. I could pick an n of 10. Right? I could animate, here's a random sample of 10 data points, find the mean, and plot that mean. And if I did this a bunch of times, right? So for any size n, I could choose any size n, and the distribution of sample means will be approximately normal, and that's what this first piece says here. All right, so if the population is normal, the central limit theorem says that, right, central limit theorem, I struggle writing today, the central limit theorem, let's call this part 1, basically says if the population is normal, say is normally distributed, then the sampling distribution of sample means will also be, right, is also normally distributed. Now, the central limit theorem goes on to further state the relationship. And we can see it over here in symbols, and I'm going to write it over here. So this says that the mean of the distribution of sample means is going to equal the mean of the population. So again, if I were to write that in words, this is the mean of the distribution of sample means. That's going to equal the mean of the population. Now, the standard deviation of the distribution of sample means is equal to the population standard deviation divided by the root of the sample size. Now, where this really comes from, we don't typically use this, is that the variance of the distribution of sample means is 1 over n. It's like the average of the distribution, the sampled standard deviation of the population. Now, in our language, we typically call this the standard error. Let me scroll down a little here. All right, so I'm going to change color. This is the standard error. So we're going to call this the standard error. And again, what this really is this is the standard deviation. This is the standard deviation. I'm going to get lazy and abbreviate. Standard deviation of the sampling distribution. Okay? So, Part 1, Central Limit Theorem says, if my population is known to be normal, then I can take samples of any size that I want. And the distribution of sample means is going to be normal. And the property, right, the relationship is that the mean of my sampling distribution equals the mean of the population. And the standard deviation of the sampling distribution, we call the standard error, is the population standard deviation divided by the root of the sample size. So part 2 of the Central Limit Theorem says what our visualization was for the second graph. So we did the skewed right graph. We did a bunch of samples, and we noticed when our population wasn't normal, our distributions of means was still approximately normal. Let me clear this. Let me do, I'm going to do custom. I'm going to make kind of a crazy distribution here. Here's something that's bimodal. Let me do sizes of 25, and let's do a whole bunch of samples. So, even though my population is not normal, my distribution of sample means is normal, and our means are going to be pretty much the same. Now we can see the mean of that crazy population I drew is 12.07, and the mean of my sampling distribution of sample means is also 12.07. So in every textbook, right, we're going to see something similar to this, that for any shape population, my distribution of sample means will also be normal. Now, technically, mathematically speaking, in order to guarantee that the distribution of sample means is normal from a non-normal population, we need sample sizes that I will say are large. Now, in this particular textbook that I stole this graphic, that threshold of quote-unquote large is samples of 30 or more. I've seen other textbooks that say that threshold is 50. Conceptually, the idea here being we want to sample as large as we possibly can. Right? So if we're doing an experiment or we have some funding, hopefully I have enough money to take a relatively large sample. Now, something kind of interesting here, when you get a prescription for some medicine, the prescription will come with some information. And most people typically don't read that information, but part of that information tells you about the experiment that was done to determine the effectiveness of that medicine that you're being prescribed. And if you read those details, they will tell you the sample size. So they'll have a control group, they'll have an experimental group, and they try to get as large samples as possible. They're usually in the thousands of people. And the reason that we sample, or that they sample with such large sizes, is we want to make sure that whatever the population distribution is, that we're guaranteeing that our distribution of sample means is normal, and we'll use the standard normal relationship. Now, even though this textbook says that large threshold is 30. Another textbook I've seen says the large threshold is 50. What's interesting in this simulation, let me clear all of this, is I don't even have a size of 30 or 50 to choose here. So even if I choose 25, my sample distribution is still normal. And in fact, I think I forgot to change this the first time. I had a sample size of 10. Oh, I didn't want to animate that. But I'm still going to get a normal distribution. Now, that doesn't mean that you should ignore the statement in your textbook. We should still go by the statement in the textbook. And again, that concept being, we want samples large enough. All right, so again, just like we did, let's write this down. So for the central limit theorem, let's say part 2. It says for any shape population, right, the distribution of sample means will be approximately normal. I'm just going to say will be normally distributed. For samples large enough, for samples that are large. Okay, and again, most textbooks say that threshold is 30, some say it's 50. Pay attention to your textbook. Now, I still have the same relationship that the mean of the distribution of sample means is equal to the population mean. And again, we don't know the mean of the population, right? That is the whole reason for sampling. So when we do our sampling distribution, whatever the mean of that sampling distribution is, we're going to infer that the mean, that is also the mean of the population. So again, I do not have access to the population. I can sample from the population. Whatever the mean of that sample is, I'm going to infer the mean of the population is equivalent. Now, I'm not really assuming. The central limit theorem really guarantees this for me. So I know that this relationship is true, that the means are equal, or at least really, really close to each other. And again, the standard deviation of the sampling distribution, we call that the standard error, is the standard deviation of the population divided by the root of the sample size. So again, this is going to be the basis of everything else we do throughout the rest of, our statistics course here. So in this section, what we're doing is introducing this concept. We're visualizing this concept, and then we're going to do some problems where we apply this concept before we take it into a deeper process. So let's take a look at a quick example just to apply the concept, and then we'll take these problems to a little bit more interesting of a level. So I stole this out of a textbook so I could copy and paste without having to write all of these words. So please stop the video, pause the video, and write this example down for yourself, and then unpause and come back, and we'll do this together. All right, now that you're back, this example says that a study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours with a standard deviation of 1.4 hours. Random samples of 100 sleep times are drawn from the population, and the mean of each sample is determined. Find the mean and standard deviation of the sampling distribution of sample means. Then let's sketch a graph of the sampling distribution. All right, so we are given information here. Let's say we know that the mean of the population is equal to 6.8, and the standard deviation of the population is 1.4 hours. And we're being asked to find the mean of the sampling distribution of sample means. So the mean of the sampling distribution of sample means we know will be equal to the mean of the population, which is 6.8 hours. Now let me stop for a second. If I'm drawing my distribution of sample means, how do I know that my sampling distribution is normal? How do I know that this is normal? Well, part 2 of the theorem says as long as my sample sizes are more than 30, then the distribution of sample means is normal, regardless of the shape of the population. So this is normal since n is greater than or equal to 30. So I jumped to this result a little prematurely. So we know our distribution of sample means will be normal since our sample sizes are large enough. And in that scenario, the mean of the sample distribution equals the mean of the population. And then the standard deviation of the sampling distribution is the standard deviation of the population, which we know is 1.4, divided by the square root of the sample size. So this is 1.4 divided by 10, which is going to be 0.14 hours. Okay, so if I draw this graph, I sketched a rough normal curve. Here's my mean, which is going to be 6.8. And then I know that the standard deviation of the sampling distribution of sample means, man, that is a mouthful, is 0.14. So if I do 6.8 plus 0.14, I got my calculator in my hand. Here is 6.94. So I'm 1 standard deviation above the mean. Here's 2 standard deviations and 3 standard deviations. Keep in mind, this is a z of 1, this is a z of 2, and this is a z-score of 3. So my next z of 2 here is going to be 7.08. I didn't give myself enough room. This is bad board management. And then my 3 standard deviations from the mean is going to be 7.22. And then I would continue that process to the left. So I'm going to do 6.8 minus 0.14 using my calculator. That's going to be 6.66. I'm going to write that up here. So there's that 1 standard deviation below. And then I'm going to subtract 2 standard deviations from the mean. I'm going to get 6.52. And then I'm going to subtract 3 standard deviations from the mean. And I'm going to get 6.38. I want you to practice one for me now. So again, I've copied and pasted a problem from a Pearson textbook by Ron Larson and Betsy Farber. And in this problem, it says the training heart rates of all 20 years old athletes are normally distributed with a mean of 135 beats per minute, standard deviation of 18 beats per minute. Random samples of size 4 are drawn from this population and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution. Then sketch a graph of the sampling distribution. So I want you, first of all, to do what I was supposed to do first in the last example and justify why you can use the Central Limit Theorem. So what am I told within this problem that tells me my sampling distribution of sample means will be normal? And then go ahead and find the mean and standard error and sketch the graph. So pause the video, try this on your own. When you're done, come back. We'll take a look at this together. All right, how did you do? Well, now that you're back, let's take a look at this together. So first of all, how do I know that my sampling distribution of sample means is going to be normal? Well, part 1 of the Central Limit Theorem says if our population is known to be normal, then our distribution of sample means will be normal for any size n. So we're told here that the distribution of the population is normal. So even though we have sample sizes of 4, which isn't more than 30, we still know the distribution of sample means is normal because the population is normal. Now, since the central limit theorem guarantees my distribution of sample means is also normal, we know the mean of the distribution of sample means equals the mean of the population, and that's 135 beats per minute. And then we know the standard error, which is the standard deviation of the sampling distribution, will be the standard deviation of the population divided by the root of the sample size. So I have 18 divided by root 4, which is going to give me 9. So then doing a rough sketch of a normal distribution representing the standard deviation of sampling means, I have my mean of 135 that we have here, and then my standard deviation was 9, so I add 9, add 9, add 9, and then I come back to my mean and I subtract 9, subtract another 9, subtract a third 9. So the mean is my z of 0. I have a z of 1, z of 2, z of 3, and then z of negative 1, negative 2, and negative 3. So in these two problems, we're just applying the concept of the central limit theorem. If our sample sizes are 30 or more, then we know the distribution of sample means is also normal, where the mean of the distribution equals the mean of the population, and the standard error is sigma over root n. And then in this example, we used part 1, where we didn't have sizes of more than 30, but since the population was normal, then we could still apply the central limit theorem. Now, to be honest with you, what's kind of unrealistic here is knowing the population is normal. That's typically not the case. So what we're going to do in the next videos is we're typically not going to know that information unless we have some prior knowledge of data sets of this manner. For example, it's pretty well known that the heights of humans is roughly normal. So if I'm looking at the population of heights of humans, I'm going to know from prior experience that that property is typically normal for a sampling of that type of, or I should say for a population of that type of data set. Now, let's take a look at a couple other examples where we take the next step here and we find some probability. All right, let's take a look at an example where we're going to actually take this to the next level and calculate some probabilities, right? So these would typically be word problems applications that you would look at in a section where you're discussing the central limit theorem. So this example says the average number of pounds of red meat a person consumes each year is 196 pounds with a standard deviation of 22 pounds. So if we have a sample of 50 individuals that are randomly selected, find the probability that the mean of the sample will be between 193 and 200 pounds. And again, in this section, I want to point out to you something that is somewhat unrealistic, is that we're given information, we know information about the population, and we're inferring information about our sample. What we're going to do in the future videos is we're going to have information about the sample, we're going to infer information about the population. But for now, we're getting our hands dirty with the central limit theorem, right? We're just applying the concept here. So first of all, how do I know that the mean, how do I know that my distribution of sample means is approximately normal? Correct. My samples are of size 50. So I have samples of size 50. So samples of size 50, which is greater than or equal to 30, right? Guarantees by the central limit theorem that the distribution of sample means will be normal. The distribution, I'm going to get lazy, of sample means is normal. Okay. So we know that the mean of the distribution of sample means is equal to the mean of the population, which we were told in this case is 196 pounds. We know that the standard error of the distribution of sample means is the population standard deviation over the root of the sample size. So for this particular problem, that's 22 over the square root of 50. And this is going to give me about 3. I'm getting 3.11. So I just pause the video real quick to crunch onto my calculator, and I'm getting about 3. All right, now just like in the prior two problems, if I do a rough sketch of my distribution of sample means, here's my mean of my distribution of sample means, and we're getting 3 as the standard error. So if I add 3, add 3, add 3, and I'm going to get what? 199. It's going to give me 202 and then 205, right? And then subtract 3, subtract 3, subtract 3. So I'm going to get 193. I'm going to get 190 and 187. So this question is asking me, what is the probability, right? What is the probability that the mean of the sample will be between 193 and 200? Now, keep in mind, this graph is the mean of the distribution of sample means. And then coming back to the simulation real quick, right, remind ourselves, right, if I'm taking samples of size 50, which I can't do that here, and I animate, right, here's all my data points, and then once I calculate the mean of all of those data points, I plot that mean. Now here's that mean. So the question is asking, within the larger population, the larger distribution of sample means, here's that distribution, what's the probability that my one sample mean fell right there? So in this case, we're looking for the probability that my sample mean falls between 193 and 200 pounds. So the question here is, what is the probability? What is the probability that my sample mean is between 193 and 200 pounds? And visually, right, this is really going back to our prior sections. So I'm finding the area under the curve between those two bounds. Okay, pause the video. I wanted to scroll. So if I do this by hand using the standard normal table, I have to find the probability that my sample mean is at 200, and that's going to give me cumulative all the way down, and then I have to subtract out the probability that my mean is less than 193. So doing this again using a table, what's the probability my mean is less than 200, and I'm going to subtract the probability that my mean is less than 193. And if I'm doing this on a standard normal table, I need to convert each of these to z-scores. So what's the z-score for a value of 200? My mean was 196, my standard deviation was 3. And that gives me 1.33. And then if I find the z for 193, this one should actually be pretty easy, right? Because that's negative 3 over 3, which is negative 1. So in terms of a table, we're finding the probability that my z-score is less than 1.33 minus the probability that my z-score is less than negative 1. Now I need to look up 1.33 in my standard normal table, so bringing that up, here's 1.3 and my second decimal place of 3. So 1.33, I get 0.9082. So I get 0.9082. I get 0.9082. And then I'm going to look up a z of negative 1. So looking up a z of negative 1, I get in my table, here's negative 1.0, and then the second decimal place of 0.0 is the last column. So I get negative 1.00 is 0.15. So that was 0.1587. So the overall probability here. Subtracting those values, I get 0.7495. So again, my interpretation is taking a sample of 50, the probability, my mean of my sample lies between 193 and 200, is going to be 0.7495. Now, if I'm using technology to do this, and we talked about this in the prior video, I'm going to move a little quick. So if I'm using a TI, I'm going to go to the distributions menu, so second vars, and I want a cumulative probability, normal, CDF. So my lower limit was 193. My lower limit was 193. My upper limit was 200. My mean was 196, and my standard error, the standard deviation of my sampling distribution, was 3. So that was a typo. So there's 3. So lower, upper, mean, standard deviation. I'm getting 0.7501. Now this is a little bit different. I'm getting 0.7495. Remember that the table is not as accurate as the technology. So if your expectation from your instructors, you're doing this by hand, obviously 0.7495 is your answer. Most online math systems, like my math lab, my stat lab, will accept both answers. So just keep that in mind. If I'm using something like StatCrunch, a particular publisher type of tool, so just like we talked about in the prior video, I'm going to go to Stat, Calculator, and I have a normal calculator. And once I bring that up, right, I want to go to the between feature, and my mean was 196, my standard deviation was 3, and I'm looking between 193 and 200. So there's a 0.7501, again, technology being a little more accurate. And then finally, if I'm doing this in Excel, I'm going to type in my entry bar, hit F of X, and I'm going to start to type normal. Where's it at? Norm. I think if I do norm, it'll pull it up for me. Okay, so I forget which one this is. Normal dist returns the normal distribution for specified mean and standard deviation. So I want to specify the mean at 96, standard deviation is 7. So I'm going to double click that. Right? So my mean is 190. So actually, remember, in Excel, I'm forgetting, I have to subtract the two. I literally have to type in this here because Excel doesn't have a between feature. So I'm going to go between 200 and 193. So my X is 200, my mean's 196, standard deviation's 3, and it is cumulative. Click OK. So that's the cumulative to the left, 0.908. Now remember, the table gave me 2. This is giving me 0.9087, 9.88. I'm going to subtract, and then again, I'm going to do normal dist. And then my X value was 193. Standard deviation was 3. Oops. 193. The mean was 196. Standard deviation 3. And yes, this is cumulative. And there's the 0.7501 the technology is giving me. This is everything in this video. This is the introduction to the Central Limit Theorem, an extremely powerful and useful tool that we will use throughout the rest of the course to draw inferences from a sample about the population. I look forward to seeing you in the next video.